Good evening from Mountain View, California. What we will cover today is the first video of the IViewOps services series. Services is technical services to a plant, consulting services, operations services that you may provide. So the difference between the services and the plant series is that in services you are setting up a configuration for the plant or for your own engineering analysis, and you will go back and forth with the plant to fine-tune it, and then at the end of it you will deliver it to the plant for the plant to use as part of the plant series. Now, what I would recommend is that before you go through the services series, please look through the intro video for the plant series and at least the first 3 of the plant series. So that means video 1, 1A, the dashboard, and how to run alternate scenarios. Actually, that's 4 videos of the plant series. So the intro plus 4 videos of the plant series, please look through them so that you're at least familiar with how IViewOps can be used. So what I'm going to do is I'm going to start with a blank screen, and my objective is to get to this IViewOps plant which we use in the class, and then in some of the subsequent videos we will add the solids handling system such as an anaerobic digester. We will add a sludge holding tank. We will discuss an aerobic digester. We will also discuss different types of thickening such as gravity thickening and DAF, and recycle from dewatering and other solids handling processes. Now, we will also talk about in the dynamic simulation data feed. If you have familiarized yourself with the plant videos, you notice that at the KNSG plant we use the 30-day average. At some other plant we may use a 15-day average or a 10-day average, such as the one in Cinnaminson, New Jersey, which is a higher rate plant, to set the data or to feed the data to IViewOps for the steady state. Now, if you're just doing it for engineering analysis, you need not use an Excel link. But I will show it to you because down along the road it gives you flexibility. So here we'll work with SI units, but we also have the flow in MGD. So we are using 10,000 meter cubed per day, 15-day average flow, a wasting average of 115 meter cubes per day, a DO in each of the aerobic zones of 2.65 milligrams per liter. You can use different DOs in different zones. We will talk about turning the air on and off in one of the anoxic cells. And if you want the flows in MGD, here's the flow in MGD and the WAS in GPM. In dynamic simulation, we will also cover the trend line of the influent flow, which you can see over here, and an EQ basin in one of the subsequent videos where we are doing partial equalization, and so we have the partially equalized stream here. We will cover variable wasting rate over a 24-hour period. For example, here you can see the wasting rate go from 100 to 150 meter cube per day flow rate, and then back down to 100. We will also cover variable DO set points at different times of the day. And lastly, we will discuss turning air on and off in an anoxic cell like cyclic aeration, much like what you saw with the blower in the KNSG plant where they're turning the blower on and off. It also comes up in aerobic digesters, in SBRs. Okay. So this gives you a feel of how we will tie into dynamic simulation. Now the dynamic simulation, in this case, you see we have 96 time steps for a day, but you can go for a longer period, like you can go for 7 days. You can even change the delta in time to 5 minutes or 15 minutes or 2 hours. But as you go above 15 minutes, you start losing the accuracy that you would need if you were doing optimization on the plant. So you may do it for 2 hours. The model is a very accurate model, but in a 2-hour time step, you obviously don't get the granularity that you would get with a 15-minute time step. Now, going down to 5 minutes can be an overkill for most plants if you have a long enough detention time, but in some instances you may want to go down to 5 minutes, like if you were simulating an SPR and you wanted to be very accurate with the simulation. Okay, so back to where we will start and where we will end up. We will end up with this plant, but we will start with a blank slate over here. Now if you scroll over modules, and you can dock this. So if you're a new user, you can decide, okay, I want to go to this and I want to dock this. And when you dock it, the modules will show up right adjacent to this. If you are an advanced user, you will not need it. You can keep it undocked and save more of the space over here. Now there are two influent, there's a simple influent and a complex influent. We will not start with the complex influent, but you can read it up in your user manual. By the way, there are 4 parts to the user manual, so please make sure that you look through part 1B, 2A, and 2B in addition to part 1. Now, the influent complex is part of the expert series. Not all of the expert videos will be on the site. Then there is the management and asset management series. Not all of those videos will also be on the site. But we will definitely post the simpler ones, like the influent simple. We'll start with that. So what I did was I went over here, I pressed the mouse and the left mouse, and I put it down here. So you can have more than one influent. So I'm pressing the left button of the mouse and I'm dragging the icon onto the screen. If you decide you want to delete one of these, you click on it and go to the delete here, and it'll ask you, and you can delete it. Again, I go here and I can delete it. Okay. Now, as soon as you put it in, you'll see it show up in the asset hierarchy. Now, in IViewOps, asset hierarchy is important because ultimately, if you read through the website, we are synchronously optimizing the plant's assets and the processes. And why is that important? Well, if you want to really optimize a plant, not do a dummy design type of an optimization or a partial optimization, you need to know which asset is operating at what time and what the aged capacity is. Now, an asset that is 10 years old, like a blower that is 10 years old, is not necessarily going to have the same airflow at the same power consumption as a blower that is new. So the asset ages, and if you want to truly optimize, you need to bring in the assets and their capacities and blend it together such that the assets tie into the processes. Well, here we put in the influent, and within the influent you'll see that there are 2 child assets. There's a flow controller, and then there's a lab, and within the lab there are multiple assets. Each lab parameter is treated as a real or a pseudo asset. Okay, now if I want to rename this, I can call it raw influent or some or something else, whatever the name is in your country. Whatever the convention is. So here is the raw influent. The next is, what is this flow controller? Well, the flow controller is defining what the flow rate is. Now, if you are a simple user, you can just enter your flow here. Okay, my flow is 10,000 meter cubed per day. We will talk about the time series later on in a separate video, how you set up a time series. Now, in the plant videos, you saw that we had linked up the flow to an Excel file, and that is a strength of IViewOps, to be able to do these links, because as you get to more and more sophisticated use and want to give the plant more flexibility, you would like to tie in to these external files. So if I wanted to tie in to an external file, what would I do? Well, you go through a two-step process. First, you go find the file to attach it to. So I clicked on this attach thing, and then it looks for a file in the folder. Well, right now what has happened is I don't have any file in this folder, so it doesn't know where to go look. But once I press on the green plus sign, which I did over here, this green plus sign, it opens up a folder where I was. And right now I'm going to use this influent pattern 1, which I think is this Excel file. Yes, it is called influent pattern 1, and I'm going to use that and link up to that. So I click on this and I say open. And it'll go through the link up process. And here's the path to that file. Well, once I've done this link up, then I can go here and say, yes, I'm going to link this up. And once you link it up, you can say, okay, you can select which file. You can select which sheet in this file. Here we are selecting sheet 1. If I look up which cell, it's cell E4. So I'll go here and I will define the cell and say cell E4. Okay, so now what does this link do for me? Well, let's test it out. Let's change the influent flow rate from 10,000 to 9,000. What we have to do is we have to save this file. So I've saved it. Now let's do a data import. So to do a data import, like you saw in video 1 of the plant video series, you click on import and you click on the start button. We are doing a manual import. So it goes through the import, and if there are no errors, it'll say 0 errors, and you can see that the flow rate is 9,000. I'll change it back to 10,000 now that I've shown you how that works. Not 1,000, but 10,000. And I have to save this again because IViewOps always reads the saved version of the file. And I'll go through over here and I will click import again and I will import the new value. And you can see it's back to 10,000. Okay. So I call this the raw influent. If you want, you can rename this flow controller to be the RI raw influent flow controller. The lab values. Well, you have a default set of lab values which are more on the dilute side. You may want to enter lab values for a much stronger or the stronger influent. Let's say the TSS is 250. Let's say the VSS is 230. Now you should have this lab data handy before you start this exercise. Let's say the volatile fatty acids in this influent, if you have that data, is around 25 milligrams per liter. Let's say the fermentable COD, not all of the influent soluble COD will be fermentable. And by the way, the particulate COD can go through hydrolysis and fermentation. But let's say some of the COD is in some form that is not fermentable. So let's say 75% is fermentable. Okay, so what is the soluble COD? Let's say the soluble COD is 200. What is the total COD? Let's say the total COD is 450. Now, you have soluble non-biodegradable COD and particulate non-biodegradable COD. Let's say these values are 10 and 15. Okay. Ammonia, nitrate, ammonia, SKN, and TKN. Well, we need to enter that, but right now, if I enter an ammonia greater than the SKN, it'll give me an error saying that, okay, you have entered the value must be less than or equal to 17. Press escape to continue. So what I do is I first do the TKN. Okay, let's say the TKN is 40. Let's say the SKN is 25. And let's say the ammonia is 22. Okay. Then I have this SKN, non-biodegradable, etc., OP, TSP, TP. Okay, let me leave those alone. Let's say the alkalinity is 250. Okay, and the pH is, we'll leave it alone for now at 7. Now you can get into more details. You can enter the dissolved oxygen. For example, in the raw influent, there's a default value of 1. You can enter if you have some microorganisms in the raw influent, like if you have some XOHO of 5 milligrams per liter, you can enter that. If you have an OF of 1, you can enter that. But it's not necessary. You just need this top section. Now, there is an ITSS by XS. For now, we will check this to use this value of ITSS by XS in the global model. Now you may then ask me, well, how did you get this BOD number? Well, the BOD number comes from another location, and for now I will show you where that location is. You go to model, you go to parameters, you go to SGM, which is the suspended growth model. The BGM is for the biofilm growth model, and the PCM is for the physicochemical model. You go into the BGM, you go into conversion factors, and here is the biodegradable COD to BOD factor. Okay, let's say this is at this point 1.75, so I've saved it. We will get familiar with this as you get into the expert series. Now, if I run this, it will update the BOD, but I've not run it as yet, so it does not update the BOD. Next, we want to do some parts of the headworks. So let's say this plant has a screen. Put in a screen, and if you want, you can rename it and call it, okay, raw influent or influent screen. And you will see that it shows up in the hierarchy. It shows up with a default amount of solid separation. If you want, you can change it. Let's say you have 0.2% of the suspended solids, some particulate matter getting separated here. If you have a pump station, you can put in a pump station, but we'll keep life simple. Grit chamber. Now, a grit chamber is interesting in that this is the first time you'll start seeing a tank. Okay, let's call it grit removal process. Okay, now within the grit removal process, you have what we call a tank group. Actually, it'll be a tank group. If you have more than 2 grit tanks, it'll be a tank group. Now, how do you add 2 tanks? Well, IVops is asset-based, so it's important to get into the field of building the assets. So now I want to add a second tank. You go in here under cells, you click on this 3 dots, and it says rectangular cell. Well, if this plant has rectangular grit chambers, go ahead and continue with it. If it has circular, then you would put in a circular grit tank. So let's say this is a rectangular tank, and there is a rectangular grit cell, and there is a second one. So I go in here and I put a rectangular cell, and now I have 2 rectangular cells. Now within the tank, first you will see the depth of the grit tank. Depth of the grit tank is usually about 2 meters deep. Then you have to, so let's call this grit tank group. Okay, now let's call this grit tank 1. It's called rectangular cell, which is the default. So, okay, a grit tank, this tank may be 5 meters long, and it may be 1 meter wide. 1 meter is, or it may be half a meter wide, let's say. Okay. Now, we won't go over this connectors for the grit tank, but I will point out something over here, that you can define whether a tank is on or off. You can either connect it to SCADA, and SCADA will define whether it's on and off over here. If I click on this value here can be linked to an Excel file which is fed from SCADA. Or you can go in here and say this grit tank is offline. Okay, grit tank also is offline for maintenance. So if it is offline for maintenance, it'll be offline anyway. So you have this 2 status, available and unavailable. The available, unavailable stands for maintenance. The online, offline stands for whether it is online or offline. And so this other one is grit tank 2. So as you will see now, I have changed the dimensions of both of these tanks and the tanks are set up. So we have had the screening, grit removal. We can put in an equalization basin, but right now I will defer that to a more advanced video. Then let's say we have a primary clarifier. You put in a primary clarifier, and once you put in your primary clarifier, there are a few steps you have to go through. First, when you're initially running the model, within each tank, if the tank has a biological model, you can turn the model on or off. Well, until you calibrate, until you converge the initial model, let's turn the primary clarifier off. Now, I will show you what I've done with the primary clarifier in the other video, but for now, let's continue over this. We will talk about how you can set a local model for the primary clarifier because it helps with the convergence. For example, your primary clarifier over here, when we go to SGM, you could decide that you want something local to this clarifier, and you can select your local model, and within the local model you can have your local coefficients which may be different from the global. Okay, but for now I'll keep this at global. Now you also have the ability to have different processes turned off, and for example over here we may decide we want local processes in the primary clarifier. Like if you want the fermenters to be working, XOF to be working, but not the methanogens, you can turn this off. If this plant you don't expect biological excess phosphorus removal at all, you can turn this one off, and so on and so forth. So you can have local processes. So we'll keep this process at local. You can define the presence removal of solids in the clarifier. Now in the more advanced model, you will find that the removal rate can be made variable, but right now we will just keep it constant. And the variable rate can be a function of flow, a function of chemicals that you add to the primary clarifier if you have advanced primary treatment, like adding chemicals to enhance primary treatment. Here's the depth of the primary clarifier. Let's say it's 4 meters deep. Okay. Now we get into setting the child assets for the primary clarifier. The first is underflow. Well, the underflow is essentially the primary sludge flow, so I'll call it primary sludge flow controller. Sludge flow controller. Okay. Now, the primary sludge flow controller, obviously this default value is incorrect, and you have to select the units. But let me look what I have done since I already set it up. I'll look here. What did I set up as the primary sludge flow controller? I set it to 50 meter cube per day. So I could go back here and essentially set this to 50 meter cube per day. Okay. Since I've already done this elsewhere, I'll set this up. Now, in a dynamic simulation, if your primary sludge flow is changing at different times of the day, you can enter the time series data. Okay, so we will connect all this, but the easiest way to connect in IViewOps 2 is click on this, then click on the next one, it'll connect that, and then click on this and click on the next one, it'll connect these two, and so on and so forth. Now, if you want to give this a name, this flow stream a name instead of the default name, call it raw influent. So this is the raw influent flow stream. This one is the screen RI screen effluent. This one is the grit effluent. So I just am erasing this, press delete, and then grit effluent. Okay. Now let's look at what is here. When I run it, if I just want to save steady state data, I do this. If I want to also save the dynamic data, I click on this. If I want to optimize and save optimization data, I will click on this. Now the reason we don't keep everything clicked is so that the results file does not become too large. Now, if you want to change the color, go in here and select the color you want for your, let's say, your influent or your headworks flows. So here I'm coloring this to be this color over here. I could set this guy also to be the same color if I want. I could set the color of this too. And what the colors help you do is it helps you keep things grouped together in a much easier fashion. Now, down below over here, I know that my primary effluent is going to mix in, I know from having set up a plant, is going to mix in with the return sludge. So I'll have a flow combiner over here. In this flow combiner, it'll combine the primary effluent, which is coming over here, with a RAS, which is going to come back through here. So I may call this flow combiner PE and RAS combiner. Okay. Now this is primary effluent. I may want to color, and I may want its data from dynamic simulation also to be included, and I may want to color it different so that I can distinguish what is a primary effluent from what is raw effluent. So you can see the color is different, and I want to name it right now. I'll click on this, and I will name it primary effluent. I delete this guy, and I name it primary effluent. So now you can see primary effluent over here. Okay. Now I get to the activated sludge tank. Now there are different options you have. You can select a bioreactor. You can select a biofilm bioreactor if it has biofilm in it. You can select a plug flow bioreactor, and if you select a plug flow bioreactor, you can break it up into different cells, and you can put biofilm in it. And you also have sequential bioreactor and membrane bioreactor, etc. over here. Now there are some like chemical feed or a pump station over here or a flow equalization that you can put in any part of the plant. It's not like the flow holding tank for your treated wastewater. That means the treated effluent has to be over here. We can move it around, but that's for the more advanced user. So let's put in a bioreactor, and here is a bioreactor. Now let's say this plant has 3 trains. By 3 trains means there are 3 parallel trains in this plant. Now you could have put in one reactor for one train, another for another, another for another, and have a clutter of assets showing up on the screen. But what we do is a compromise. We want all the assets in here. We want to be able to show if the plant is operating with one less train or one less tank somewhere, that it reflects in the setup for that day so that we can simulate it accurately. But what we are going to do is we show one object, but within that we will have multiple cells for the multiple parallel trains. So let's say this is the anoxic 1. So anoxic zone 1. Okay. Now here I'm keeping the model on, and let's say the depth is 4 meters. Okay, so that's the depth. Now this I will name to be the anoxic 1 tank group. Okay, and within the tank group I'll have the 3 parallel trains. So this is anoxic 1 train 1, anoxic 1 train 1. Okay, now what is its length? Let's say its length is 5 meters and its width is 4 meters. Okay, now, and let's say it's online and available. Now I know that there are 2 other trains, so how do I get to it? Go back to the tank group, go back to this 3 dots here which I talked about for always for trains, and add in 2 more parallel rectangular cells. Okay, rename this anoxic 1 train 2, get its dimensions right, 5 meters by 4 meters, and then rename this guy anoxic 1 train 3. And get its dimensions right too. Okay, so now let's say today we are not operating train 3. Okay, we don't have enough demand, we are not operating it. You can go in here and turn it offline, or you can connect it to an Excel file, and the Excel file can take data from SCADA. So we have turned it offline. So now we have turned it offline. If you go here, you will find that there are 3 trains, but 2 are online and 3 are available. Okay. Now, how do we go inside the anoxic one and say that, okay, the air is turned off? Well, there are 2 ways to do it. You can go in here under diffused aeration, and if there are no diffusers here, you just have a mixer and you cannot turn the air on, you can say none, and you can see that it has turned itself off. Okay. Now let's say you have a second anoxic zone where the air may be on, the air may be off at certain times of the day or at certain times of the year. So I'll put in another another bioreactor here, and I'll use, let's say it is also 4 meters in depth, and I'll go through the same steps. I'll come back. I'll first finish setting it up, and then for sake of time, I'll show you how I set up the diffusers. So as far as the anoxic zone, the tank group and all, it's all the same as tank 1. So what I've done is I've defined each of the cells, put in its dimension, I've turned the third one off. Now as far as this anoxic zone, here let's say I have diffusers, and depending on the time of the year or time of the day, I may keep the air on. Let's say it's alpha because it's in the front end is 0.5, okay, when the diffusers are on. Let's say this is membrane fine bubble, and this is a standard efficiency at 3.65 meter depth. I will show you how to assign blower groups in a more advanced video. This may be part of the expert series. But in IVops, you do also replicate the equipment that is there, all the pumps and all the blowers, all the dewatering presses is replicated so that we have a complete asset hierarchy, and if a blower is out, how it affects the rest of the plant, or if a pump is out, how it affects the recycle and how much redundancy you have. That is all simulated. So it's very different from those in that sense who use BioWind, GPSX, or one of those. It is an asset-based model. To be real, one has to be asset-based, and optimization is truly has to link up assets and processes. That is the whole philosophy. Okay, so now if I open up the diffusers, you have 2 things here. You have a set point for the diffuser, which is a DO set point, and you have an on-off controller. The on-off is is the air on or off. Okay, let's first do the on-off controller, and let's say the default is off. That means that it is off, but in a dynamic simulation, we can turn it on and off based on a feed coming into the model, a data feed coming into the model, which will come in through here. So it is off. Let's say the set point controller is 2 milligrams per liter. We could say it's 2.5, or we could also link it up to data from an Excel file. And in an Excel file, we may have different columns, different cells for different cells of the plant. So if I wanted to link this to an Excel file, I'll say yes. I'll say which file. In this case, it's the same file here. I'll say which sheet, and let's look where this data is, and let's just use this DO data in J4 for all the cells, just to make life simple. So I'll say J4, and now if I press the import button, it went through the import, and you can see that DO has come in here. Okay, now that DO will apply only when the air is on, but in the set point controller, in the on-off controller, I have said that under steady state the air is off, so the air will be off. Now similarly, I go add in the 3, let's say there were 3 or 4 dedicated aerobic cells after this, so I will go in here and I will put in my aerobic bioreactors. Okay, I'll put them here for now, and let's say I had 3 of these aerobic bioreactors, and each will have 3 parallel cells to represent the 3 trains. So now let me do something. Let me go down below and bring in a secondary clarifier so that we can discuss a secondary clarifier. Now As I mentioned, you can have a biological model in a secondary clarifier, which will be in the sludge blanket. You can also separate out the clarifier stilling well and separate out the clarifier clear liquid, which we have done at the KNSG plant, which if you look through the intro video, the plant intro video, you would have seen. Okay, now TSS removal. Okay, you can have variable rate where the rate varies at different times of the day based on the flow rate, or you can have a constant rate. I'll just select a constant rate for now. Let's say this clarifier is 5 meters deep, okay, or let's make it a little bit more complicated, 4.5 meters deep. Okay, now the secondary clarifier has an underflow controller, which is the flow coming out of the bottom of the secondary clarifier, but it also has the tank group. So let's call this secondary clarifier tank group. Now, how many secondary clarifiers do you have and what is its shape? Well, the default is circular, but you can have a rectangular clarifier. That's not a problem. Oh, in fact, we should have done it for the primary, but we'll go back to the primary after we finish the secondary. Okay, let's say we have 2 secondary clarifiers in this plant. Okay, so how do we go ahead and do that? Well, you go in here and select this 3 dots, and then you add and you select circular cell, and now you have 2 circular cells. So the first one is SC clarifier 1, secondary clarifier 1, and you have to enter its diameter. Let's say this one is, well, I'll keep it at 15, but I'll check what I used in the other model for the clarifier. Let me see here. If I press on it, let's see if we entered some values for the secondary clarifier tank group. Secondary clarifier 1 was 30 meters. Okay, so let me also use 30 meters for now. Okay, let's say this is 30 meters. Okay, now there's an on-off controller. We'll keep it on right now. And let's say there is a second, here's the second secondary clarifier. So let's set this up. 2. And this guy is also 30 meters. Okay, so now we have these 2 secondary clarifiers. Now, I talked about the primary clarifier and the primary clarifier tank group, which we had not set up, but let's say we want to now set it up. Primary clarifier tank group. Okay, and let's say this plant has rectangular primaries, and there are 2 rectangular primaries. So then you go in here, and what you have to do is you have to delete the circular and then add and select rectangular, and there are 2 of these, so we have 2 rectangular cells. So now you have 2 rectangular primaries, and you have to enter the dimension. So let's say they are 30 meters long and 7 meters wide. Okay, I'm guessing at the dimensions. I should actually figure out really what the dimension should be. Primary clarifier 1, and here's primary clarifier 2. .30 by 7. Okay. Now we have a few things to add. Okay, where does this sludge go? Well, for now, we will use a sludge terminator. We won't put in the gravity thickener, and we will not put in anaerobic digester, but we will just take the sludge out as if it's coming out over here. Now you can move this around, and if this is a sludge flow and you want to color it differently, let's say this is a sludge and I want to color it, what should I color it? I can color it this for now. Okay, that's my sludge flow here. I can connect these guys up. Oh, I've forgotten to add in a nitrate recycle, so I should add in a nitrate recycle system. So how do we do that? Let's quickly look through and add in a nitrate recycle system. Okay, so you go down here, the nitrate recycle, we have tried to save on space. What you do is you can put in a flow divider. The nitrate recycle is actually going to divide up the flow. And I can decide that I am going to put my nitrate recycle inside this, and I want to flip this. Let's say it's called flip horizontal. Okay, let me see if I can make more space for this thing over here. There'll be a nitrate recycle coming in over there. Here are my 2 cells. Here is my my 3. So I'm moving things around, pressing on the left mouse and dragging it, left mouse button, and then dragging it around. And here's my nitrate recycle. Okay. Now, as you see over here, the same icon is showing up here. So ultimately, you will not need this. But let's say this nitrate recycle comes in right here, but I want to make a little bit more space. So click on this, and you can drag this up. Okay. Now, this nitrate recycle is going to combine with the flow here, so I have to put in a flow combiner here. I'm going to flip this, and I want to move this gently, so I want to nudge this, so I can press this button and nudge it a little bit. I want to flip this. I use I think I flip vertical. Oh, flip vertical went the wrong way. Flip horizontal. Now let's start connecting the flows. This connection is not allowed. Why is it not allowed? Let me see what happened. Okay, here these two are connected. This flow is going in here. This flow is going in here. This flow is going to go here. This is going to go here. This is going to go here. And this is going to go here. And this recycle is going to come from here back to here. Now, what is the capacity of this recycle system? Well, if you look here, well, it's called a divider, but I will call it nitrate recycle. Let me call it what it is. Okay. So here's a nitrate recycle. It has one asset called the flow controller. So this is the nitrate recycle flow controller. And let's say we are going to operate this nitrate recycle at 40,000 meter cube per day. You can connect it to Excel. Right now, I'm just doing it this way. So 40,000 meter cube per day. Okay. If I want to create a little bit more space here, you can see a little bit more space over here. Now, this nitrate, the effluent from here comes in and goes into the clarifier. Okay. Now, what do we do with the flow coming out of the plant? Well, we can have filters, etc., but just to for this services first video, I'll just use this, and this is my, let's say, my secondary effluent. So this was my secondary clarifier. Now, for those of you who want to become an expert, you can add in your equipment here. You go into the equipment module and you say pump group. And since this asset is selected, now a pump group, nitrate recycle pump group is going to get added. It asks, do you want to create an asset over here? And there, you can see a nitrate recycle pump group get created. So here's your nitrate recycle pump group. Now, within this pump group, you can have multiple pumps, more than one pump. So go back here. You see the pumps. Now, a total number of pumps 1. I want to change it. Let's say there are 3 basins and 6 pumps. So I keep adding, and I get to 6 pumps. And you can have the capacity of each of the pumps, and you can connect the pump status. Pump can be online, offline. You can connect the pump status to SCADA, etc. You can put in the true capacity of each pump. Let's say each pump is 10,000. Let's say each pump is 10,000. Okay, so I can have each pump, I can call it NR train 1 pump 1. The next one will be NR train 1 pump 2. Train 1 pump 2, and so on. Okay. What do we do with what is coming out of the bottom of the clarifier? Well, we are going to have a sludge wasting. So I'm going to put in a sludge wasting for the waste sludge. So go here, and I'm going to use a flow divider, and this flow divider is pointing the wrong way, so I'll do a flip vertical, and now it's pointing the right way. I'll connect this to this, and then I'll connect this RAS line here. And I'll set up the waste sludge here, but I also need a sludge. Right now I'm not going to put in a sludge holding tank. That's for a more advanced video. I'm just going to take the sludge out this way, as if it is getting hauled out of the plant. I'll call this flow divider WAS flow splitter. I'll go into its flow controller. I'll call this WAS flow controller. And I can link this up to Excel and bring the data in if I want. So here's my link up. Sheet 1, and let's look in Excel what that cell is. It's cell G4. So okay, I could put in G4, or if I didn't want to do it, I could put in the flow rate directly here. Or it's actually 115, but I typed in 100, but let's put in G4. Now if I have put in G4 and I press import and I do import it, it should change that value from 116 what has it done? Anyway, I need to check on this why it did not change the value, but anyway. Okay, here's the flow 115.1. I'm trying to, why is it 115.1? Is that what the value is here? I think the value here is 115.1. There you go. You see the value over there, 115.1. Oh, I'm in the wrong file here. Let's go back to this file. So here's a waste sludge. Now, within the clarifier, secondary clarifier, we haven't finished with it. You have to set up what is your RAS flow rate. Well, I could put in the RAS flow rate here of 5,000 gallons per day. Let me see if I have it in my Excel file. Well, I don't have RAS data. So right now I cannot connect up to this Excel file, but I'll enter it directly over here. So that's my RAS flow rate 5,000. It's not linked to Excel. Okay. Well, actually it's RAS plus the WAS flow, but then here's my WAS flow that is over here. Now, one other piece of information that is required for the clarifier is under its lab, the unstirred SVI. If this plant is operating at an SVI of, let's say, 110, and I usually use a 7-day average of SVI and feed that in if it is operating within the plant, as you saw in the KNSG plant. That's where the SVI gets in. So now, I can go back in and change the color of this. So for example, on the sludge lines, if I want to save it for dynamic simulation, I'll do that. If I want the color to be changed, open up this, go here, I'll use the custom color, and let's say the sludge line is this color. Okay. This sludge line, I'll also color it similarly. It is this color. This waste sludge line, color it similarly, is this color. Okay. Now we get into an interesting thing here. We should name these guys. This is secondary clarifier underflow. Okay. This is RAS. And as I am renaming it, you'll see that it is getting renamed in the hierarchy. Now there are a lot of flow streams here which are yet to be named, but we will run into an issue pretty soon, which is the hierarchy may be in the wrong order, and we would prefer to reorder it. Let's say this is secondary effluent, and I want to color this. Let's say I also want to save it for dynamic simulation, and I want to color this blue. Okay, so I have the secondary effluent here. Now let's look at. Let me go ahead and rename all of this, and I'll come back to the recording. Okay, so let's undock this guy so that I have more space here. I really don't need it anymore, and I can use the scroll bar at the bottom to get back here. Okay, now let's say like you can see the sequence of data, and let's say I wanted to move this nitrate recycle from after aerobic 3 to before this guy over here. Now this is a little painful, but you have to press the left mouse and move it one at a time. Okay, so move it one at a time, up, and now my nitrate recycle has been repositioned. Now, I haven't colored these lines, but ideally I should go ahead and color these to be of one color. So let me go ahead and do that. So now you see that I've colored it and all of these are showing up together. And let's say if I want to move the primary sludge where it is with the waste sludge, I could do that, but for now I'll leave it over there. Okay. Now it seems like the waste sludge color should have been a little different. Let me see if I can get back to, okay, I'll do the waste sludge color to be this. Okay. Now, if I want to move this line around a little bit, go click on the line, grab its middle, move it up. There it is. Now, for the sake of time, I haven't as yet done these reactors. So the next thing is I need to make sure I put in all these strains, etc. correctly. And then the other thing is I need to save this file. So I'll save this file, file save as, and I'll call it IViewOps service 1. Okay. Services 1, as if we are providing consulting services to set up the plant. So here it is. So now I have saved this file. Now rather than go through and drill through this file, I'll switch over to this file that was already set up. And this file has been run, but if I want to run it again with these values, I just go here and I click the run button. So if I go here and I click the run button and then I click start, it's going to start running. Now, the faster the computer, the faster it'll, the better the computer, the faster it'll run. Now, when you do a run, you have a few options. You can define the maximum number of iterations. Here I've set it to 20,000. You can set the evaluation frequency. Initially you may set it to 99. I've increased it to 299. Maximum allowable error, it can be 1,000. Sometimes I increase it to 10,000. And this is a factor that is used to reduce it, an error factor, which keeping it to 0.201 or 301 is a good enough number. Now you can start with a new initial guess where the plant will begin from all these initial values and start to converge. Now, I need to point out a few things. You can start, if you are using scenario analyzer, you can define which scenario from which you start your guess. When you run reruns, you put in a value a little bit greater than 1, like 1.001, so that there is some perturbation put in so that the model can converge back when you ask it to reconverge. It doesn't think that nothing has changed. That perturbation causes a little bit of a change, shakes it up, and it allows it to converge again for a new set of values. If your change is very small, otherwise it would think that there was no change in value, so we put in that perturbation. Okay, let me see where I should go next. We will cover dynamic simulation separately. Let's talk about a little bit about the components. You can have different components that you can turn on. And here you can see that since I'm not using methanol, I've turned off the methanol component. You can have different factors. I don't have digesters here. I've turned off the obligated anaerobic methanogens, and I'm not using methanol, so I've turned on the methanotropes. I'm also not using iron or aluminum or a digester with struvite, brucite, etc., so I've turned those off. Okay. No point turning it on and slowing the model down. You want it to be efficient. As far as processes, what processes am I running? I'm running OHO, OAF. I've shut off OAM, which is the methanogens. I've turned on PAO. I've shut off MET, which is the methanotropes. I've kept AOB and NOB on. Okay. Now, parameters, SGM parameters. what we have found is that the default values for in the mid-Atlantic, in the U.S. Wastewaters, these decay rates are a little high. We lower it a little bit, so you will see these decay rates are, well, an oxide decay rate for OHO to be also a little lower. Okay, now what else? I'm going through it quickly because this is more advanced, but if you go to AOB, we find in the US waters the KO2 to be less than the default value of 1. The K ammonia, we have set it at 0.55. Same thing with NOB, we have set the default value of KO2 to be 0.5. Okay. There are other things like hydrolysis things and stoichiometry. But there is an interesting feature in your model. If you want to save your SGM file, you can. And you can say, okay, I want to save it as this value, SGM class 1, and it'll save it. So, and okay, it already existed. And what you can do is you can bring this SGM file into another plant. You can do the same thing with BGM, which is for the biofilm growth. Okay. So we press the run button, and I showed you the run for this video. Now, once you run it, you can go and click on any flow line like you have seen in the plant videos, and especially plant video 2, where we also do the dashboard. You can see all the values here. You can see it for steady state in dynamic simulation. You won't see the values for the flow lines, but you will see it in results, and you will see it in the dashboard. So that about ends this setup over here. You can very quickly look at, okay, how much mixed liquor? I had 3,300 mixed liquor. How much ammonia? 0.2 ammonia. How much nitrate? 6.8 over here, etc. What was the clarifier underflow concentration? That was 9,800 milligrams per liter. If you want to know what was the distribution of microorganisms in that 9,800, so much of XOHO as COD, so much OAF, AOB, NOB, etc. If you want to know what the COD components are, that's over here. The XX, XI, etc. is the same convention as ASM2D. If you want the chemical precipitates, well, there isn't much here, but there is XI. Okay, in the COD, the precipitates are here. Because we were not adding ferric or aluminum, we don't have those precipitates. So let's stop the basic video here for the plant, for the services. So this is video services 1. We will cover dynamic simulation in